I'm going to do a series of 4 different videos to talk about how to solve force problems when you have a diagonal. And each video is going to get increasingly more difficult, and really it's just focusing on a new algebraic trick. But from this video, the first one, you'll learn how to figure out how to solve problems with diagonals regardless of how difficult it is. All the other videos are really just going to talk about different tricks after this. So in order to solve, right, we need to be reminded of our 6 steps to solving problems, right? We need to get context, draw a force diagram. We need to list our variables, both known and unknown. We need to make a custom equation using F net equals ma. We need to take that equation and solve, and then we need to make sure that the answer makes sense. Alright, so let's solve this problem together, and we'll use all 6 steps. Using a rope, you drag a 55 kilogram crate along the floor with a 300 Newton force at a 50-degree angle with respect to the normal. The coefficient of friction is 0.32. What is the acceleration of the crate? Okay, so from this we can see the context is that the object is accelerating. It sounds like it's accelerating on a flat horizontal surface, so it's accelerating horizontally and not vertically. And so we know there's going to be a net force in the horizontal direction of some kind. Next, we draw our free body diagram. We can identify the different forces. I know there'll be a force of gravity or weight downwards. There'll be a normal force upwards. There'll be a force of friction in the opposite direction of motion along the surface. And there'll be a force of, I'll call it tension, in the direction that the person is pulling, since he's pulling with a rope. Now, something you should keep in mind is that on a test, when they say draw a free body diagram, this is what you're going to draw. You're not going to draw anything with like split up forces, or you shouldn't put any numbers on it. When they ask on a test to draw a free body diagram, you draw this and you leave it alone. Now, I don't know about you, but I use my free body diagrams a lot of times to solve. I'll put numbers on and things like that, and we'll do that here this time too. But if you're going to do that, draw this and for the test. And then you can draw it, just draw it again, but this time use this next one to solve for whatever you need. Also, another really important thing is to note is that in the past, once we draw a free body diagram, then we proceed on, but we can't really proceed on because we've got a diagonal force. And it's really hard to find the net force horizontally when this force is kind of pulling sideways and kind of pulling up. So we can't move on if we have a diagonal force. So what we're going to do is we're going to change the steps ever so slightly to problem solving. So before we had our 6 steps, and we still have our same 6 steps, but we're going to kind of like add a 2.5. And that is, if you have a diagonal, you're going to also recreate another free body diagram, but this time you're going to make a working free body diagram. Now what I call a working free body diagram is simply a free body diagram that has no diagonals, and any diagonals you used to have, you've split them up into just horizontal and vertical components. Alright, so let's make a working free body diagram together. The normal, force of friction, and weight are all orthogonal forces, and we're all good with that. They're all either up, down, left, or right. Tension is the only diagonal, so we're going to split it up. We're going to draw the horizontal and vertical components. So I've kind of redrawn the whole diagram over here for just making a useful working one. I'll draw a vertical component and a horizontal component for that force. It goes up this much and over that much. Alright, and now we want to figure out those quantities. One is going to be the tension force times sine of theta. One's going to be the tension force times cosine of theta. That's what it always is. Let's see here. The red one here is adjacent, so it should be cosine, because cosine is adjacent and hypotenuse. And the green one is sine, t sine theta. Alright, so we've split it up, but you know, this is looking kind of ugly. I don't need all 3 of these forces here, and I don't really like to draw my forces like this anyways. This force is kind of like off the box. It's kind of goofy. And I don't need this diagonal anymore, because really I'm replacing this diagonal with these 2 orthogonal forces. Orthogonal, by the way, means basically up, down, left, right. Okay, so I'm going to get rid of the diagonal, right, because I'm replacing it with these 2, and I'm just going to draw it in a way that it looks like any other free body diagram I might have. Now this problem is no different than anything else you've solved so far. The only difference is from what we used to have is that there's just no diagonals, and we've only got up, down, lefts, and rights. So we're ready to solve just like we do any other force problem. Before we start coming up with the equations to solve, since we have some numbers and we can actually calculate some forces, let's go ahead and do so. For example, the component vertically, t cosine theta, we have t and we have theta, so we can go ahead and plug and chug, and we find that the t cosine theta is going to equal 193 newtons. T sine theta will equal, when we do the math, 230 newtons, and the weight will turn out to be equal to 540 newtons. Of course, calculating weight using the equation mass times gravitational field strength, G. Now that we have these quantities, we can go ahead and start making some equations to solve. Now, we're going to do this by simply making a custom equation by writing an expression for the net force in both the horizontal and vertical directions. So let's start with the horizontal direction. I know there will be a net force, and that the forward, because it's accelerating forward, and so this force here, t sine theta, must be greater than friction. So we're going to write an expression. T sine theta minus the friction will give us whatever leftover net force we have. We'll replace net force with a way to calculate it, which we know is ma. So we get t sine theta minus force of friction is equal to mass times acceleration in the horizontal direction. Hence the sub x. That means in the horizontal direction. Okay, we can do the same thing in the vertical direction. Now, it's not moving or accelerating up or down, so this total force vertically should be 0. So we're going to write another expression. The two forces upwards together, t cosine theta plus normal force, minus whatever you have downwards, should give you your total net force in the vertical direction. We know that total force is 0, and so we can rearrange and just say, hey, look, these two together, t cosine theta and normal force, equals the one force downwards, weight. Now, we've just created two customized equations, one for the horizontal direction, one for the vertical direction. Anytime you're doing any problem, you need to create these two equations because it's going to help you solve for whatever you need. Now, sometimes you don't need them both, but it is so useful to just, when you have a force diagram, just make those equations. It's so fast and easy, and oftentimes you do need it, and you never know when you will. So I'm just in the habit, I always just make it regardless. Alright, now that I have some equations, I want to use the equation from the horizontal direction in order to solve, because that actually has the variable I'm looking for, acceleration. And I'm going to go ahead and plug in what I can. Let's see here. I know t sine theta, so I could plug in that, but you know what? I don't know the friction yet. That's a bit of a problem. So actually, before I start plugging things in, I've got to solve for the friction first. Well, I know that the frictional force is equal to the coefficient of friction times the normal force. So I could go ahead and just plug in normal force, right? Normal force is always equal to mass times gravity, right? So I go ahead and plug that in, and now if I do that, I'm going to get everything wrong. Let's talk about this. This is the most common mistake that people make when they're doing diagonal forces, is that they always assume that the weight is equal to the normal force, because in a lot of cases that is true. But let's look at this. The weight here is 540 newtons. If this normal force was also 540 newtons, that would mean that I've got 540 plus 193 upwards and only 540 downwards. This object would be accelerating upwards. That makes no sense. Remember that equation we wrote out earlier, comparing these three forces together? I don't know why, but people forget to look at that equation, and they just forget about this vertical component. The fact that it was diagonal, it has a vertical component. So let's examine that one more time. The equation we made in the vertical direction was that these two forces together equals the weight, 540. So normal force is actually a little bit smaller than the weight, right? Because some of it's being supported by the rope itself. So with this equation here, I can solve for normal force. I rearrange, and I have normal force is equal to the weight, which we know, minus the t cosine theta, which we also know. So we can do some math, plug it in, and we get the normal force is equal to 347 newtons, not the aforementioned 540. So I'm going to get rid of this old statement, and I'm going to replace it with the correct normal force. And I find that the force of friction now is 111. Now that I know the force of friction, I can plug that in my equation before, and I can go ahead and finish my problem, and I get an acceleration of 2.46.